Refraction of light. Okay, first we have to know what is refraction. Refraction is when a light travels from one transparent medium into another transparent medium, it gets bent. Okay, the bending of light is called the refraction of light. So here there are two diagrams. So when the light travels from a rarer medium to a denser medium, it is bent towards the normal. So here this is the normal and it is bent towards the normal. Okay, so next diagram, here the light travels from the denser medium to the rarer medium, then it bends away from the normal. Okay, so here the speed of light is different for different medium. Okay, so that is more in rarer medium and comparatively less in denser medium. So for example, so when the light enters a denser medium, the speed reduces. So, okay, here the speed is more, and when it comes into a denser medium, the speed automatically reduces and it bends towards the normal. Okay, and here when the rarer medium, okay, its speed increases and it bends away from the normal. Okay, so refraction of light through a rectangular glass slab. Here in this concept, first let's consider a rectangular glass slab. Okay, here when a ray of light passes through this rectangular glass slab, here the refraction occurs twice. Okay, so first when the light ray enters the glass slab from the air, okay, so from air to glass, here is the first refraction takes place, and second one when it exits from the glass slab to the air. So this is the second. So here the refraction occurs twice. Okay, here it can be clearly seen, and here this is the angle of incidence. Okay, this is the incident ray, this is the normal ray, and here the angle formed is the angle of incidence. Okay, then here is the refracted ray with the normal. So this is the angle of refraction. So again this is a refracted ray. Okay, here the angle formed is angle of emergence. Okay, here let's see the distance. This is the distance, okay, between the perpendicular distance between the emergent ray and the incident ray when the light passes out of the glass slab is called the lateral displacement. Okay, laws of refraction of light. Here the first law is the incident ray, refracted ray and the normal ray to the interference of two transparent media at the point of incidence all lie in the same plane. This is the first law. And in the second law, the ratio of the sine of angle of incidence to the sine of angle of refraction for light of the given color is always constant, okay, for a given pair of media. So this law is also called as Snell's law of refraction. So sine I by sine R is equal to constant, and this constant is called as refractive index. Okay, refractive index. So the absolute refractive index of a medium is the ratio of the speed of light in air or vacuum to the speed of light in a medium. So this is called the refractive index. So the relative refractive index of medium 2 with respect to medium 1 is the ratio depends on the speed of light of the medium 1 to the speed of light in medium 2. Okay. Spherical lenses. Here first we have to understand what is lens. So lens is nothing but it is a transparent medium. Okay, it is bounded by two surfaces, one or both which are spherical. Here the spherical lenses are of two main types. They are convex and concave. So first we are going to see about convex lenses. Convex lens is nothing but it is the converging lens. Okay, it has the name converging lens because it converges a parallel of beam of light rays passing through it. Okay, it all meets at the point F after refraction. Here next, in concave lens is also known as the diverging lens because it diverges a parallel of light rays passing through it. Okay, here this rays of light parallel to the principal axis after refraction, it gets diverged and appear to come from a point on the principal axis on the same side of the lens. So we are going to see some of the definitions related to lenses. Here the first definition is the pole. Pole is a center of the spherical refracting surface of the lens. It is called pole and it is a point where the principal axis meets the surface of the lens. The second is the optical center. The center point of the lens is called the optical center. Next is the centers of curvature. Centers of curvature they have mentioned here. Consider two imaginary spheres. So the centers of the two imaginary spheres of which lens is a part in between are called the center of curvature of the lens. Okay, a lens has two centers of curvature. Okay, because it has two curved surfaces. Okay, next is the principal axis. The principal axis is the imaginary line that is passing through the center of curvature and the pole. Okay. The next definition is the aperture. The area of lens suitable for refraction is called the aperture. Okay. The aperture of lens is the effective diameter of its light transmitting area. Next is the radii of curvature. The radii of two imaginary spheres of which the lens is a part is called the radii of curvature of lens. Okay. Here a lens has two radii of curvature. Okay. So they may or may not be equal. And next, focal length. The focal length is nothing but it is the distance between the optical center, that is the center of the lens, and the focal point of the lens. This is called the focal length. Next is the power. Power of the lens is the reciprocal of its focal length. Okay, the SI unit. Okay, the SI unit of the power is diopter. So refraction by spherical lenses. Here we are going to see some of the image formation in lenses using ray diagram. For drawing ray diagrams in lenses like spherical mirrors, we consider any two of the following rays. Okay, so the first is the convex lens. When we consider a convex lens, a ray of light is parallel to the principal axis. Okay, after refraction it passes through the focus. This is the focus on other side of the lens. But in concave lens what happens is it appears to diverge from the focus on the same side of the lens. So next, in a convex lens, a ray of light passing through the focus after refraction, it goes parallel to the principal axis. This is the principal axis and here it goes parallel to the principal axis in a convex lens. But in a concave lens, what happens is that a ray of light directed towards the focus after refraction goes parallel to the principal axis. This is the principal axis and it goes parallel to the principal axis in a concave lens. So in the third diagram here, in a convex lens and a concave lens, when a ray of light passing through the optical center goes without any deviation, okay, it doesn't deviates anywhere. So likewise in a concave lens, here when this light passes through the center of the lens, that is the optical center, it goes without any deviation. This is the third diagram. So here we are going to see the images formed by a convex lens. Okay, here the object is placed at the infinity. So the image formed is at focus f2 point. Okay, here this image is highly diminished, real and inverted. This is the nature and size of the image. So in this diagram, when the object is beyond 2f1, that is the object is present beyond 2f1, that is it is at only finite distance. Okay, here then the image will be formed between f2 and 2f2. Okay, here this image will be diminished, real and inverted. This is the nature and size of the image. In this diagram, when the object is present at 2f1, the image will be formed at 2f2. Okay, it is the same size as that of the object, and here the image is real and inverted. And in this ray diagram, we are going to see when the object, okay, when the object is between 2f1 and f1, the image will be formed beyond 2f2. Okay, so the size and nature of the images, it is enlarged in size and it is real and inverted here. And in this diagram, here we are going to see the object is present at f1. So the image formed is formed at infinity. Okay, so the image will be highly enlarged, real and inverted in this case. And here when the object, okay, when the object is present in between the f1 and O, that is the optical center, the image will be formed on the same side of the lens. Okay, this image will be enlarged in size, virtual and erect. Erect means it is in the upright position. Okay. Next, we are going to see the images formed by the concave lens. Okay, in the first case, we are going to see the when object is present at the infinity, the image will be formed at focus f1 on the same side of the lens. So the image will be highly diminished, virtual and erect. And here when the object is between the infinity and f1, that is at finite distance. Okay, here the image will be formed between, the image is formed between the f1 and optical center O on the same side of the lens. So this image is diminished in size, it is virtual and erect, that is upright position in this ray diagram. Then we are going to see about the sign convention for spherical lenses. Here the sign convention for spherical lenses is same as that of we have already seen for spherical mirrors. Okay, except one thing, that is the distance are measured from the optical center. Here the distance are measured from the optical center, that is the center of the lens. Here the focal length of the convex lens is positive. Okay, here it is positive and focal length of concave lens will be negative. Okay, here in this diagram we can clearly know that the height upwards will be calculated as positive, and when it is coming downwards it is considered as negative, and then the distance toward the right will be always positive and the distance towards the left always it is considered as negative. Okay, so these are the things we have already seen. Lens formula for spherical lenses. Here the lens formula for spherical lenses is the relationship between the object distance, image distance and focal length. Okay, the lens formula is given as follows. Here 1 by V, V is the image distance, minus 1 by U, U is the object distance, is equal to 1 by F, F is the focal length. Okay, next topic is the magnification produced by spherical lenses. Here magnification magnification for spherical lenses is nothing but it is the ratio of the height of the image to the height of the object. This magnification is denoted as M is equal to H of I. I means image. H of O. O means object. Okay. The magnification is also related to the object distance and image distance. Okay. It can be calculated or expressed as follows. V by U is equal to magnification. Okay. We are going to see about the power of a lens. How to find the power of the lens. Power of a lens is nothing but it is the reciprocal of its focal length. Okay. It is given in meters. Okay. So here this is the formula. So P means power of a lens is equal to 1 by focal length, okay, in meters, or F is equal to 1 by P. Then the SI unit of power is diopter. It is denoted as capital D. 1 diopter is the power of the lens whose focal length is always 1 meter. Okay. Here the power of the convex lens is positive and the power of the concave lens will be negative. Okay. About the power of a lens. How to find the power of the lens. Power of a lens is nothing but it is the reciprocal of its focal length. Okay. It is given in meters. Okay. So here this is the formula. So P means power of a lens is equal to 1 by focal length. Okay. In meters, or F is equal to 1 by P. Then the SI unit of power is diopter. It is denoted as capital D. 1 diopter is the power of the lens whose focal length is always 1 meter. Okay. Here the power of the convex lens is positive and the power of the concave lens will be negative. Okay.